Alright, so let's go ahead and focus on energy. We're going to be talking about kinetic energy, potential energy, and then we'll also be talking about this thing called the work kinetic energy theorem. Let's just go ahead and jump in, and we're going to derive an equation to start off. So in this unit, we've talked about that work equals force times distance. Well, actually, there is a very close connection between work and kinetic energy, or energy in motion. And I want to show you that. So we know that work equals force times distance, but we also know that F equals ma. So force equals mass times acceleration. So if we plug that in, instead of force, we have mass times acceleration. And it's displacement. We used S in the first semester, but since we've been using D with work, I'm just going to continue using D here. So we got work equals mass times acceleration times displacement. But then, also in 1D motion, we learned that v squared, or final speed, equals u squared plus 2 times acceleration times displacement, which we used as S, but in this case I'm going to use D. All right. And let's just go ahead and rearrange this equation a little bit, and then plug it back into our original equation. So what I'm going to do is I'm going to subtract u squared to the other side, so v squared minus u squared equals 2ad, and then I'm going to divide by 2. So what I'm left with is, I'm just going to flip sides here, ad equals v squared minus u squared all over 2. And if you notice, we have AD in this equation, and we also have AD in this equation. So I'm going to plug in this v squared minus u squared all over 2 into our work equation. And that comes out to look like work equals mass times the quantity of v squared minus u squared all over 2. And then I'm going to distribute the m and rewrite the equation. And the final equation looks like this. Work equals 1/2 times mass times final speed squared minus 1/2 mu squared. And what we've found here is actually very important. So this quantity right here, if you see, the only difference is final speed and initial speed. But this quantity right here is actually the equation for kinetic energy. So we're just going to stop there, and we'll come back to this in just a few moments. And we're going to skip down to kinetic energy. So we kind of already mentioned this, but kinetic energy is energy in motion. All right, so when we're talking about kinetic energy, an object will have some speed. Okay. So we've already derived the equation, but the equation looks like this. Ke, standing for kinetic energy, is equal to 1/2 mv squared. Right, where Ke is kinetic energy, m is mass, v is speed. Right, kinetic energy is a scalar, so that means we're not going to have any direction. We're not going to have positive, we're not going to have negative. Right, we'll just get a number, a magnitude. Right, so what are the units? Kinetic energy, it's energy, and if you remember back to electricity, all energy is measured in joules. So if you notice, going back up here, work, what is work measured in? Well, it's measured in joules. And then 1/2 mv squared, it's going to be measured in joules. So joules equal joules here. And then mass is still kg, measured in kilograms, and speed is meters per second. Okay. So pretty simple equation there. Now let's go back to our work kinetic energy theorem. So we derived the equation to look like this. We can rewrite it as work equals Ke final, because v is final speed, minus Ke initial, which is initial kinetic energy. We can also rewrite the left side of the equation, so work we can rewrite it as FD equals the same thing. We can rewrite it as mgd, right, mass times gravity times displacement, equals the change in kinetic energy. Right, we could also rewrite it as mu k, so the coefficient of kinetic friction times mass times gravity times displacement equals the change in kinetic energy. So any of these I could write. You could write the change in kinetic energy, so the change in would be final minus initial. You could rewrite it the full way, mv squared minus 1/2 mu squared. All right, or you could rewrite it as this: final kinetic energy minus initial kinetic energy. All right, so this equation can change quite a bit just depending on what you're given. All right, so you can start to see if you get this equation right here, there's quite a few variables that you're going to be given. You could be given mass and displacement, and say it started at rest, you're trying to find the final speed. So that's kind of one of the examples of a question. Units, right? Units, work still in joules, and kinetic energy in joules. All right, so you can just kind of work through there and plug that in yourself. Potential energy is energy that is stored. I didn't switch colors, but oh well. So the equation, we actually have two equations for potential energy. Because if you come down here, there's two main types of potential energy that we'll talk about. We'll talk about gravitational, and we'll also talk about elastic. We'll mostly focus on gravitational during this unit, but we'll come back in a later unit and focus on elastic potential energy. So our equation for gravitational, so I'll just put G, is PE, so potential energy, equals mass times gravity, and we'll plug in a positive 9.8 here, times height. So potential energy, once again, it's going to be in joules, mass in kilograms, gravity in meters per second squared, and height in meters. Okay, so pretty simple equation. And then our other equation would be for elastic, so I'll write that out. And it would be potential energy, and sometimes you'll see a small subscript E, and this one you'll see a small subscript G. All right, but most of the time we'll just leave those off. And our equation for elastic potential energy is 1/2 K times X squared. K here, elastic, we're talking about things like a rubber band, a bow and arrow, a spring, anything that you pull back and you're storing energy. So that K is like how strong is that rubber band, how strong is that spring. And then X represents how far did I pull it back. Right, and that would tell you how much elastic potential energy is in that object.